Okay, and we want to find a power series solution to this second order differential equation about the ordinary point x equals 0. Okay, let me. Okay, letting you copy here. Okay, one moment, everybody. Where did I put it here? One moment. Yep, there it is. Okay, so let's see what we have here. So, okay, we have this second order differential equation, and let's remind ourselves what a power series solution looks like. And notice it's about the point, ordinary point x equals 0. So the power series solutions based on that are going to be of the form where n equals 0 to infinity of c sub n times x minus 0 to the nth power. Okay, in other words, the x sub 0, okay, the x sub 0 is equal to 0. And I think for pretty much all the problems in section 6.2, which you have where you have to find power series solutions, they have the ordinary point x sub 0 equals 0 because it's just easier than to work through the power series, because then the yeah, Matthew likes that. Yeah, this then is just going to be x to the nth power. Okay, now I will section 6.2. I will just mention this. I do need to post the assignment for that, but you already have an assignment posted for 6.1. The part where you find a power series solution. So, but I will get 6.2 posted. Certainly, when you wake up tomorrow morning, it should be there. Okay, if some of you are done with that other 6.1 assignment. I figured you're focused on the exam, but I know some people might be done with that. Okay, so let's go ahead here then and move forward. So, okay, well, all right, this is our power series solution then. And I'm going to take the derivative of the power series solution. Okay, I'm going to take the derivative of the power series solution. And we know from last class the derivative of a sum is the sum of the derivatives. And you've seen all this math before. Okay, you've seen it all before. We do recognize that the first term in the power series for our derivative, well, because there's an n here, well, when n equals 0, that first term of the power series drops out. So we can write the power series equivalently starting at n equals 2. All right, so
Did you mean n equals 1?
I'm sorry. I meant n equals 1. My mistake. Right. We went from the power series starts at n equals 0, but since the first term of this power series is 0, we can start the power series at n equals 1. That's correct. Yep. Thank you, Matthew. Good catch. All right. Are there any questions so far? Well, all right. So now what do we need to do? What do we need to do next? We have power series expressions for y, okay, and power series expressions for y prime, okay.
Y double prime?
That's right. We have to get it. That's right, Matthew. We have to get a power series expression for y double prime. So let me then move to the next page. So we're going to take the derivative then. We're going to take the derivative of this power series here in order to get a power series for y double prime. Okay, so let's move forward then. Okay, so y double prime is the power series of, it's the derivative of the power series for y prime, right? That's the power series for y prime. The derivative of a sum is the sum of the derivatives. And, you know, the derivative of c sub n times n to the x to the n minus first power is just going to equal this. But notice you have an n minus 1 in the terms of your series. Well, that means when n equals 1, the first term of this power series for the second derivative, the first term is going to equal 0. And so for the second derivative, you can start the power series at index n equals 2. And it's very important that you do that. Okay. Let's see, Zachary, what happened to the chain? Not sure. Are you talking this step here?
It's with respect to x, so no chain rule.
Right. That's right. That's right. That's right. You're just using the power rule, Zachary. You're just using the power rule. And so what I do now is I substitute into my differential equation the power series representations for the second derivative, the first derivative, and y itself. And that gets us down to here. Please let me know if you have any questions. I'll give you a moment to catch up here. Okay, are there any questions before we move on here? let's see. Antonio asks, why is the power series? Well, that's the general form of a power series, Antonio. When you're about the ordinary point x sub 0 equals 0. That's any power series can be written as like, here, let me highlight it here. Any power series about 0, the ordinary point x sub 0 equals 0, any power series can be expressed that way. The trick is finding the coefficients. The coefficients will vary depending on the differential equation. That's right, Michael. It's a polynomial with like infinite degree, and right. Let's see.
If it's centered around -1, is it x minus 1, or is that how this works? Or
No, this is your power series here.
no, I'm saying like if the ordinary, if it's not 0, if it's -1, you said it was centered around 0, right?
Right. If it were, let's say it were -1, then your power series would look like this: x minus -1. Hold on. If it were around -1, your power series would be like a sum. And I'm trying to, keep this mouse. X minus -1. Oh, I'm sorry. I need a C sub n, right? C sub n times x minus -1 raised to the nth power. But the thing is, this is difficult to deal with because because it's not as you're going to have an x plus 1 to the nth power. This is much easier. And
So
we want to keep it simple first.
Yeah. So like we're pretty much always going to solve these by taking that that sort of summation, and then
That's correct. That's right. That's right.
And the problems will just vary based on what functions are in front of y prime, double prime, y prime, and that kind of.
That's exactly right. That's exactly right.
That makes sense.
All right. Good question. Good question. All right. Well, so now we have a equation with power series in it, and of course we want to combine the power series. But we have a little bit of a complicating factor here, is that we have functions that are multiplying here our power series. So, well, before we combine the power series, we want to distribute these functions into the power series. We want to distribute those, like the x squared plus 1. We want to distribute that into its power series, the power series that it goes with, or that that's multiplying by, and then we want to distribute the x into the power series that it's multiplying by. So let me show you how we do that. So what I do here is I have x squared plus 1 times the power series, and I'm gonna go ahead and multiply x squared plus 1 times the power series, and then I'm gonna multiply 1 times the power series. Okay, and then add them, and that's going to get me this here. But then I have an x squared in front of that summation sign, but the x squared is not dependent on n. So I can treat x squared like a constant, and I can let me just be a little more clear here. So you understand what I did. I want to make sure I got this. I'm multiplying x squared by the power series. I want to make sure my arrows are doing it right. And I'm going to take the 1 and multiply it by the power series. Okay, and that gets me here to this second step. But then okay, I have this constant, this function x squared isn't dependent on n. So I can treat x squared like a constant with regards to the power series. that it's multiplying by, and just bring x squared inside the power series, and that's how I get the x squared right here. Okay. And then, I can take x squared and multiply it by x to the n minus 2 power, and that'll get me x to the n power. I'm going to do some simplifying. And so the first term in the equation will equal all of this. Similarly, the second term in the equation, differential equation, I have an x here, and again, the x can just be brought inside the summation, and that's going to get me then this power series here, for this series for the second term in the differential equation. Let me give you a moment to copy that down, and Matthew's comfortable, good, and we'll make sure everybody's comfortable. Let's see, Zachary says the x is not changed by the summation. Is that why step 3 can be done? That's correct. That's right, Zachary. X is not changed. Think of x as like x is not dependent on n. So you can treat it like a constant. Constants can be factored out of a series or brought into a series. Okay, now let me see. That's correct. That's right, Zachary. That's exactly right. That's exactly right. X is not changed by the summation. Oh, wait, step 4. X squared times x to the n minus 2, right? These two guys here, the base is the same, so you just add the exponents. 2 and n minus 2 makes n. Okay? Okay, let's move forward. Let's move forward here. So now I have these 3 power series, okay, that, there's my differential equation, left-hand side equals 0. Here's the differential equation again with the power series in it. I'm sorry, my differential equation, the right-hand side equals 0. And I rewrite the differential equation with the power series in it, the right-hand side equals 0. And now I've substituted in the 3 power series. And I want to combine the power series. So as you learned, we focus on the exponents. And we want the exponents to all be the same in the power series. So I'm going to let k equals n in the first and third. Oh, wait, there's another one too, right? Here's another power series. There's 4 power series, right? 4 power series that are in our differential equation. So I'm going to let k equals n for 3 of them, but for the second power series, I have to let k equals n minus 2. Have to let k equals n minus 2. Okay, and then I rewrite the power series in terms of the index k. And that gets us to this step here. Let me give you a moment to catch up. Okay, well, if there are no questions then, now what I do is, okay, I want to say this the right way. So of the four power series here, the highest index is the k equals 2 index. That's your highest index. Okay, and that is the index that's going to be the ruling index. Okay, so what I got to do is, like the second power series here, I'm going to get two terms before the power series index k equals 2 hits. So I write that second power series as this power series here. What I mean is I write out the first two terms of that. Hold on here. Okay, so I write out the first two terms of that power series, the second power series there. I write out the first two terms, and then I have plus the rest of the power series starting at k equals 2. Okay. Now for the third power series here, well, I'm going to write that power series like this. Okay. So I have the first term when k equals 1, and then I have the rest of the power series starting at k equals 2. The last power series here, okay, there is a minus there, right? The last power series I expand it out this way. I write down it starts at k equals 0, that last power series. I write out the first two terms of the power series at k equals 0 and k equals 1, and then have the rest of the power series. Okay, that's that you have to do. You have to do that. And then what we can do is we can combine all the power series. We can combine all the power series with together, because they all, so like for you know this here, okay, which is my differential equation just with power series in it. I'm going to combine all the terms that have that start at k equals 2. I'm going to combine all the power series, which I can do because they all start at k equals 2. And then what I'm going to do is the other terms that are sitting out there, this term and this term and this term and this term and this term here, I'm going to combine them the best I can. Yeah, Matthew, these are long problems. There is a lot of writing, but this is how you have to do it. It turns out that two of the terms here, this term here and this term here, cancel out. This term and this term cancel out. And that's going to leave you with 2 times C2 plus 6 times C3x minus C sub 0. So let me get to the next page, if you're okay with that. Are there any questions? First time you do it, it's some work. It'll get easier as you do more of them. But yes, these take time to do. These take time to do. Okay, so now this is my differential equation with the power series in it. And what I'm going to do is I'm going to combine all my power series. Okay, and you know, these are the terms in all my power series. And I just wrote the terms then down here. Let me maybe put it in blue. I like to use different colors. These are all the terms in the power series. And I'm just going to write those terms down here. See that? So maybe just to kind of keep things simple here, I'm underlining the terms in each of the power series. And when I combine the power series, well, here are those terms. Absolutely beautiful. And of course, the common factor is x to the kth power, right? All right, so let me give you a moment to copy down to here. If you have any questions, let me know. Okay. So we end up then, I mean, these terms here can be combined. You can combine the terms. Well, you do have the first term, ck times k minus 1 is k squared minus ckk, c sub kk. And so you have cancellation. And so if you simplify things, this is what your kth term in your power series is going to look like. And keep in mind the power series that, well, the entire left-hand side here has to equal what? It has to equal 0. It has to equal 0. So what does this mean then? Well, the only way the entire left-hand side of this equation would be equal to 0 is hold on here. Well, okay, I want to be a little careful here. So certainly you would understand that all of these coefficients of x to the kth power would have to equal 0 because, you know, x can be different values, and we would want those x values to be within an interval of convergence, right? But if we demand that that power series equals 0, the only way that could happen for different values of x is if all the coefficients of the power series equal 0. So what's happening here on the previous step, Zachary, if I distribute k k times k, and k times 1. That's k squared minus 1. So ck times k squared, I'm sorry, that's k squared minus k, right? If you take k and multiply it by k minus 1, you get k squared minus k. Well, ck times k squared minus k is just c sub k times k squared minus c sub k times k. That's how I got that part there. Now we'll have to finish this example up in the next class, but let's just continue on to the next page. I want to get there. So okay, we agree that for this equation to be true, all of these coefficients in the power series have to equal 0. So that means then what I did was I rewrote the equation. I rewrote it up here on this page, and okay, so for the equation to be true, well, you know, this term here, 6 times c3x, okay, that means c3 has to equal 0, because for if it's true for some values of x, different values of x, c3 would have to equal 0. On the other hand, also 2c2 minus c sub 0, that would have to equal 0. And then also all the coefficients in the power series, all the coefficients of your terms in the power series have to equal 0. Okay, so based on that, the coefficients of your power series, I can solve for c sub k plus 2. So this this relationship here between the coefficients with c sub k and c sub k plus 2, we can say, well, okay, c sub k plus 2 would have to equal negative k squared minus 1 times ck over k2 plus k1, right?
Wait, so how did we set things like the C3 term and the 2C2 minus C naught equal to 0 if it's just the entire thing, as in the 2C2 plus 6C3x minus C naught plus the whole power series times x to the k, you know? If that whole thing equals 0, how do we just set these individual terms equal to 0?
Well, in the power series, you're saying the whole, right, the whole, like you said, the whole left side of the equation equals 0. Well, if x can take on different values, then you have to require the coefficients always equal 0. That's the only way you're going to, I mean, you know, you have a 0 on the right side here. So, okay, everything on the left-hand side has to equal 0. Well, the only way that the coefficients in the power series, the only way the power
Oh, I
series
see what you're saying, yeah. And
0
then you use
if
that
its
logic.
coefficient.
And then you use that logic for the second term, and then you
That's
see
correct.
there's only two terms left. They don't relate to x, and since they both have to equal 0, you just solve. Okay.
You got it. You got it. That's correct.
Professor,
Oh, yes, Antonio.
why is the 1 minus k, why is it 1 minus k and not k minus 1?
Oh, what happens is here, on this step here, and we'll stop in just a moment here.
Oh, okay, never mind. You distributed through the negative.
That's right. So now at this stage here, you know, our power series solutions, we have to learn about what the coefficients are. Just like with the, you know, section 4.3, you know, hey, what's C1 and C2 I'm sorry, what are your, well, I want to be a little bit careful. In order to figure out we got to figure out what the power series are in terms of general solution to the differential equation. What are the power series? Well, the power series are defined by their coefficients. And so we're trying to find what the coefficients are. And now that we're here, the next step is we have a little bit more on the solution, but we'll continue that on Thursday's class. We'll continue that. We'll finish up this example on Thursday. Let me stop the recording.